Hello. This offline lecture presentation is about week number 7 material, which was or could not be able to be presented in the face-to-face environment at the campus due to the midterm examination. We will continue with the discussion of microprocessor architecture and programming, specifically on 8088 and 8086 chips, about the assembly code structures and approaches to perform lookup tables, and the associated command, which is a very popular command, is xlet instruction. Well, let me give a little brief introduction about lookup tables. In order to save time in the computer memory, sometimes you enter the values, usually 2-column values of the tables, in defined byte or defined word format in the data segment. So during the program execution, you don't have to calculate each value. Rather, you just get the independent variable value parameter, and then you pick up the corresponding value from the so-called table location in the data segment of the program of the microprocessor. Now, for example, you have two choices when you use, for example, a simple, straightforward mathematical function between integers, for example, a square taking operation. You can do this in two different ways. One, if you have the value, then you add a few codes of multiplication, etc., and then assigning and storing the values to some locations, so that this consumes a few lines of assembly code. Or you can prepare a kind of lookup table in specific label like square table DB, defined byte format, so that the values of each integer square is put in a specific order in an array. So this is a simple lookup table, and the name of the table is square underscore table. Then you can, during the program execution, you can access the square of any number from 0 to 9 by the use of xlet. So that's a very simple table. You can increase the number of values, but you have to be careful about M886 because you cannot continue the next line with a very long array. You have to repeat the defined byte command for each line only. So there's no, let's say, line scroll for M886. Anyway, that's a application issue. So we back to the concepts again. In order to do this, the register BX must have the offset address of the lookup table. As you remember, the data segment is pointed by the segment register related to BX usually. But of course, you can use some other registers, but that would again cost a few more lines of assembly code. And this, the number whose square is sought, must be in the AL register. So you work with AL register and the BX register for the offset value in the corresponding data area reserved for this lookup table. Then after the execution of xlet command with one line command, the AL register will have the square of the number. So the original value is erased and its corresponding lookup table value is replaced. In this specific example, it's the square. So there's an example underneath. We first move the offset of the square table, lookup table, which is the first defined in the header of the program. So the offset value of this table is set. So the first item is, or the offset value of the first item is shown. And AL5 is simply add this number to the offset to pick up the fifth element. And xlet stores this new value, picking up the square of the table from the square table data group, and then replaces this value with the original AL value. So that's so simple in the application. Similar to squares, you can also use alphanumerical characters. As you see here, let's say the ASCII codes of numbers and some characters. So actually this is an hexadecimal code conversion, you can understand. So in many microprocessor-based systems, the keyboard is not an ASCII type of keyboard. One can use xlet to translate the hex keys of such keyboards to ASCII. Assuming that the keys are 0 to F, the following is the program to convert the hex digits of 0 to F symbols, 16 symbols, to their ASCII equivalents. So again, the lookup table is created by the label ASC underscore TABL, like ASCII table, and database defined byte format starts with 0, character 0, and ends with character F. Hex value and ASCII value are two reserved, not assigned areas of the memory for the results of the lookup table operation. And the code segment is read as moving the offset value of this table to BX, then moving this value to hex value, and then code conversion or lookup table process, xlet. So there's no operation as operand for this operation, as you see. And then after the operation, now AL has the ASCII value, and this is stored in another memory variable labeled as ASC underscore value. So this program actually stores the hex value and ASCII value in two different formats after using the AL register. So the previous one was about to find the lookup table for 10 symbols or 10 characters or 10 data items or memory locations. The next one is 16. You can, of course, increase the number. And as you increase the number of parameters, then you save more time to implement the operations in the memory. So I think one operation is very illustrative with two different examples. You can also create more examples related to other operations or mathematical approaches, etc. Or sometimes the temperatures of the weather, etc., or wages, all kinds of groups of data can be used in lookup tables. Now the next topic is strings. Again, mostly used type of data storage and operation. String is an array of bytes or words having a beginning character and EOS, which stands for X end of string character. In 8086, usually end of string character is the ASCII character of $sign. Besides string array elements, it occupies a block of continuous memory spaces, exactly the same as the data structure in lookup tables as well. But these strings can be even longer, of course. And due to that end of string character, you can also create indefinite number of strings as well, or indefinite element number of strings. A string may have no elements. It just has EOS or $sign or end of string character, or it can have, say, 100,000 elements and the final element is end of string, so you can manipulate very long strings. Of course, this is not very efficient to use in 8086, but theoretically it's possible. Now the string operations are grouped in two different families. You can operate on byte strings or you can operate on word strings. Byte strings, each element is, as you can imagine, 8-bit element, and for word it's 16. Usually we don't utilize larger bit size like double word or quad word strings in 8086 environment. So a couple of commands are shown on the left side, like it's mnemonic to move a string, or next one, compare a string, or you can scan a string, or you can load a string, and you can store a string to memory. Each has its own mnemonic as 3 character symbols, and at the last 2 characters is SP or SW. S stands for string, B is byte, W is word, as you can imagine. And the operation is shown in the 4th column. In the close to pseudo code for index registers and the element number and strings. So two groups of strings, two strings are defined. One is always source, which is the original data, and the next one is destination. So DS and SI and DI and ES are the segments and offset registers are used to manipulate strings. Especially ES or extra segment is solely reserved for string operations. The principle of string operation is not much the same as general data structure, except you don't deal with single bytes or words, rather you deal with an array of bytes and words. So this is a kind of a loop action which is carried out till the end of string line is reached. Of course, during the increments of from one element to elements, the destination index registers are either incremented by 1, so the address is incremented by 1 because that's a byte variable, or it's incremented by 2, which means you've processed 2 bytes or 1 word, and then you jump to the address 2 locations after the final, or let's say the most recent operation. If we want to give an example, assembly code example, sorry, then that zoom is a little bit unfriendly about, okay, let's zoom it a little bit in. Okay. So a typical example by using the first string command, moving string in bytes, whose elements are bytes. Okay, we are neglecting the first lines of headers and offsets and message indicators, etc. First, we have to, okay, so our string is a message, ele336 lecture. It's a message which a character string, and there are 3 more characters added to the end. We will investigate their role in a few moments. So the last one is 24 hex is the code for $, which is the end of string character. So first of all, we have to assign the offset value of this MSG message to DX, because we will manipulate by using this offset value. Then we copy this to the source index register. Why do we do that? It's the topic of the most recent homework. We cannot move the offset value of data MSG directly to SI, rather because we can assign the offsets to general purpose registers A, B, C, D, and then we can copy from D to SI. Then we assign another arbitrary offset value. So this value is arbitrarily selected because we are copying exactly, moving the string to another location in the memory, and the address of the memory is arbitrarily selected to 0717. This is the segment offset address in the current data segment. And we assign this offset address, segment start address, to extra segment, and DI, which is the destination index, offset is set to 1. So actually we are moving a group of characters in one segment to another segment's start address, and this address, offset address 0717 hex. And we assign 13 decimal to CX register, which is the number of string elements, as you can see in ele336 lecture. And then with one line command move SP, everything's copied with loop command NX. So this loop command performs the act times, and the return is the end of the code. So that's related to that's the issue when we know the length of the string. But of course, if you don't know the length of the string, we have to always check the element whether it's a end of string character or not. So if we write the program in ME8086 environment and run the program, and as well we watch the memory view or memory contents from the offset value and address, etc., you see the middle or hexadecimal codes show the memory locations in byte, but their ASCII equivalents show that the original string is in the upper part and the moved or copied string is in the lower part. Arbitrarily, that was the reason that's selected to see every or two messages or two strings in the same screen. So you can also create, first of all, copy the program in ME86 and create your own moving commands, or you can load a string from a group of arrays in the memory to a specific memory location, or you can enter the values via keyboard, etc., so that they are written in the or saved in the memory, stored in the memory, the specific location. You can use or find many applications. Now, actually, that concludes most of the critical commands in assembly language of 8088 and 8086. We do have some other instructions for running, so they will not be explicitly told, but you can understand the role of these functions from their mnemonics, like escape or halt or return from interrupt or lock or no operation or wait, loop, etc. Actually, you have seen the loop command as well. So this is the point that you know all the assembly commands. Now you have all the vocabulary of 8086 to be programmed, ready to develop any program starting from the simplest or the basic ones to the more advanced one. Thanks for joining my online session, and hopefully see you in the lecture room after the holiday or vacation period is over. I wish you the best.